Okay, yep, so I'm Chris Meiklejohn. I work at Basho. You might have heard of us, we make some software. I'm going to talk about this thing that is called LASP. We're going to get into the motivations behind it. We're not going to show a ton of Erlang code, so I apologize. But it is an Erlang project. It is open source. It's on GitHub. So all of the resources are available for you to look at. And we'll look at some brief code samples, but it's more important to motivate why we're working on this stuff. So we're going to talk about distributed, eventually consistent computations. So this is my talk. Yep. And this is research that's partly my independent research along with Peter Van Rooij at UCL in Belgium. And it's part of a bigger project called Sync-Free, which is focusing on large-scale computation without synchronization. So we want to basically avoid synchronizing whenever is possible and kind of explore the application boundaries and figure out how far we can push this. And kind of what the mechanisms are that we need to make these computations work, make sure that they're deterministic, make sure that they're correct, and make sure that they're more fundamentally easier to use for programmers to reason about concurrency, consistency, and non-determinism. So we'll talk about the kind of the motivation. So what's the motivation for the work, right? So synchronization is expensive, right? If you use, you look at things like Spanner, you look at Paxos, multi-Paxos, Raft, synchronization slows things down. It takes time. You have to wait for people to agree. At the very first recon, Joe Hellerstein said, he was trying to motivate Bloom, and our work is very similar to Bloom. It's slightly, it's more functional than logic, but he motivated by saying, yeah, let's talk about synchronization. All right, everybody wait. It's like, okay, now, that is essentially synchronization, right? Everybody waits, and everybody's kind of waiting, and eventually we're going to agree on something, and eventually it's going to have the right value. But it takes time to get everybody to agree. It takes time to detect failures. We can't detect failures perfectly. And this is really problematic when we start thinking about kind of larger scale applications. This is really, really impractical when we think about Internet of Things and mobile, and I'll motivate each of those individual use cases shortly. And again, it's impractical if you want to have hundreds of mobile phones or something like that, and you want to ensure everybody gets the same state at the exact same time. You can't do this. It's effectively impractical. We need these mechanisms where we make data structures that are convergent, or we have things where we have backwards and forwards compatibility, right? You think about iTunes, right? You start up iTunes and they've changed something, right? And they're like, sorry, you can't buy a movie. You can't even download music that you already own until you wait till you get the new version of iTunes, right? So doing versioning, controlling all these things is really hard. It's really expensive. It takes time, and it puts a lot of burden on the programmer to make sure that all of this, all of these computations happen correct. So we'll talk about mobile games. So one of the use cases that the Sync-Free project is motivated by is a use case that comes from Rovio Entertainment, so the company that makes Angry Birds. So they have shared state between clients. So if Sean and me are both playing Angry Birds, and we have some state, we're logged in as the same account, Sean is going to update his profile and maybe update our profile, right, and change the name to be something like whatever, Charlie Root. And then I change the photo to be like a donut or something, right? Now we've changed that state independently, right? So the mobile app wants to allow you to make those changes independently. It doesn't want you to be on the subway and say, sorry, you don't have internet connectivity. You can't update your profile. You can't update your profile photo. That's a bad user experience. So clients are going to go online. Mobile phones are not always connected, right? Especially, you think about going on an airplane, right? You go on an airplane, you update a bunch of stuff on your mobile phone, then you get off, and now what happens, right? Do we take your state and do a round of Paxos and get everybody to agree on the right state? I call Sean, turn your mobile phone on right now because I'm about to do a round of Paxos with you. That's really bad, right? So, with mobile games, we have to ensure that state is convergent, we can handle concurrent updates, and provide the best possible user experience. And here's a little article from Rovio where they just talk about, the massive number of the massive number of users they're having and how they're scaling, and this kind of stuff motivates the problem. You think about, wow, there's so many mobile devices that have shared state on them. The second case is Internet of Things. So a newer thing, Internet of Things is kind of becoming, an actual thing, I guess. But when you think about most of these Internet of Things companies, they put sensor, so you imagine a network that has a centralized DC, you have a bunch of edge nodes, and then you have a bunch of mobile clients, or I mean sensors, right? So these sensors are going to aggregate state, and you're going to aggregate this state up a graph, right? You're going to send it to some centralized place, and they're going to compute some aggregates or something. So the interesting thing with the Internet of Things is these sensors are very low power. Sometimes they're high power. It depends. Sometimes they're offline. Sometimes, so here's a case where I live, like in, super upstate New York on a lake, and, Sean lives next to me. Sean has really great internet, and I'm a poor grad student, so I have no internet. And, we can talk through 8014B or something, right? Our sensors have 8014B. They share this information. I should be able to give my information to Sean and have him distribute it for me. But then when I come online, if I send my information back, well, how do I know if I've already seen that information, right? How do I reason if I've already observed these objects in the system? So with Internet of Things and aggregates too, compute an aggregate, send an aggregate upstream. How do I know where that aggregate came from? How do I know if I've already observed some windowing on that aggregate? Who knows, right? So again, clients go offline. These things aren't going to be online all the time. You think about how we wanted to put, Monsanto or whoever wants to deploy these things all over the place so they can monitor temperatures or something, right? In this case, they can't guarantee these things are going to be online all the time. You can't guarantee that there's not going to be some solar flare or whatever, that makes you not able to connect. So you have to inherently deal with clients going offline, duplication of state, and reordering of messages. So the Internet of Things is slightly different because here we're talking about disjoint state usually, right? Usually you have two sensors. They're going to maybe compute some aggregate together or send some data, to some centralized DC or something. So ultimately, we have this problem where we have no total order. We have no ordering on the events in the system. At best, we have a partial order usually. And this is because we allow clients to make progress independently. So me and Sean have mobile phones. We make progress independently based on some state. So we have some starting state, we make a bunch of changes, and then eventually those changes need to get merged. And this is kind of the core problem that we're trying to motivate here. So hopefully you believe me. Hopefully the mobile case makes you believe that if you don't believe in the Internet of Things case. But this is like the general idea. Offline clients, concurrent operations. And how do we deal with non-determinism? So you might say, whoa, we can do what Spanner does. Yeah, no, not really. Spanner's an interesting thing because, one of the results of this paper says that at best, we throw so much money at this problem, and the best thing we can do is synchronize clocks within a very small delta. But we still can't reason about concurrency within that delta. Well, that's fine. We can punt around that, right? And for some applications, that might be fine. But the ultimate problem here is that wall clocks are unreliable. Everybody knows this. If you don't believe this, tell me, and I'll send you like 100 articles about it. This is a core problem. And if you use wall clock resolution, such as the last writer wins strategy, based on client-supplied wall clocks, as some databases do, it's non-deterministic. You have a non-deterministic outcome. So this is bad. This is really bad. So what we want to do is stop thinking about physical time. We want to think about logical time. So I'm going to give you a little example. So I'll do a quick survey of the room. How many people here know? So most of you probably saw the React Core talk earlier, maybe. But how many people here know React Core? OK, some. How many people here know CRDTs? OK, a lot more. That's good. All right. Good, because I'm going to talk more about CRDTs than React. You can see 100 React Core talks. All right, so here, we assume that we have some shared state. We assume there's two copies of the replicas, right? So we have a replica of some data items. So we have replica A, replica B. So this is some state. We start out with some starting state. Let's pretend this is a register. So we do assignments. These are going to be the values that we assign. These are concurrent operations happening. Even though these things are kind of like located on top of each other, that's just signifying concurrency. It's saying nothing about like the actual physical time. So this is me and Sean. So here I set that. So I'm replica A. Replica A sets the object to be 1, sends the data to replica B because it's online. Replica B has got 1. So now concurrently, and concurrently can happen if you're offline. It could happen now, and it could happen now. That's concurrent, right? We're offline. We have no way to reason about these operations in the system. So we have this problem, right? When we and Sean both get online and we communicate our state, well, how do we resolve this problem here? Should the answer be 2? Should the answer be 3? So in terms of a register, this is really hard to answer because we don't really know. And a lot of systems use physical time to try to reason about how to resolve this conflict. So again, what do we do? Forgot to advance the slide. Speaker problems. So CRDTs, I don't have time to talk about a lot of them because this is a subject for an entire talk. But CRDTs are essentially data structures. So this is some research that we put into production in React. There are some other companies using it, like SoundCloud, and Mochi kind of was an early adopter of CRDTs before CRDTs, I guess. So CRDTs essentially provide deterministic resolution. They're a data structure that basically encodes this causal information and has a way to arbitrate basically which choice to make. So it's deterministic regardless of where the execution happens. CRDTs come in a number of flavors here. We have maps. So we have maps, sets, counters, registers, and graphs. So in React, you'll see maps, sets, counters, and registers, and flags. Flags are like Booleans that will move only in one direction, right? True to false, false to true. Registers can be assigned. They can contain multiple values or a single value. Counters are counters that go up and down, counters that only go up, counters that only go down, whatever. We have sets. We have sets that allow you to add something once. We have sets that allow you to add something once and remove it once. We have sets that allow you to do that an arbitrary number of times. Each one gets more complex. You imagine you can build one in terms of another. Then we have some optimized things. We have a map, which is essentially a dictionary, where you have so you can do arbitrary composition. You can do nesting. Somewhat arbitrary, not 100% arbitrary, but somewhat, given that it adheres to a very, very strict interface. And finally, we have graphs, right? So graphs would be that you contain a set of vertices and a container of edges, and you have convergence on those. So the graph one is actually really, really hard, because you want to, some of these invariants you might want to sort over a set, or, well, I don't have a cycle in the graph, or I don't want to ever have an edge that's not connected, right? So I mean, a vertice that's not connected. But essentially, all of these things provide deterministic resolution. So what CRDTs realize is this property, this is a very academic kind of thing, but it's something that we talk about here, is this property called strong eventual consistency. So in an eventual consistency system, such as if we're going to think about React with the last writer wins strategy, the not recommended last writer wins strategy, we would say that if I have concurrent updates to an object, a client supplies a timestamp, or a vnode supplies a timestamp, it coordinates them right, and then it basically chooses one or the other based on what the last writer is. And last writer is even a little fuzzy too, because it's like, well, that wasn't really the last writer, because it could be the last, it could be when that timestamp was observed. So it's really like last latest timestamp observed resolution, right? So that's interesting. So what strong eventual consistency says is that given a system where you have an object, and you have this object distributed, and you have the same copy of the object everywhere, and you have a reliable delivery mechanism that says, I will deliver a message, the same set of messages, regardless of ordering, to all copies of that object, we guarantee the correct outcome. So it's deterministic. It's deterministic in the system. Each replica has a deterministic resolution strategy. So in the literature, this is called, this is how it's kind of, this is the informal version from the conflict-free replicated, here's the citation, conflict-free replicated data types. This is from SSSDS in 2011. And it was formalized a little bit earlier than that, but this is the paper that actually has the official definition if you're interested. We say correct replicas that have delivered the same updates have equivalent state. Right? So this is a really awesome property to have in a system. As long as you have a reliable delivery mechanism, you can guarantee that everything will come out exactly the way you want it. You can reason about a distributed execution as a centralized execution. So this is great. We like this.
Do the updates have to be delivered in the same order?
They do not. They do not.
How do you know that there's not another one coming you haven't seen yet?
So yeah, so that's why this property is interesting, right? Because it assumes that once all messages are delivered, so it's as ambiguous as eventual consistency. So this builds on eventual consistency, but eventual consistency makes this like kind of a vacuous claim, like this is the Doug Terry criticism, right? Is like once all updates stop happening and all messages are delivered. Well, like when do all updates stop happening? They don't, right? So in practice. Yeah, so in practice, you kind of have to, think about this in a different way. But yes, that's a very fair criticism. So we'll provide an example. So in the CRDTs example, this is the max register. So in the max register, we'd say, well, that's fine, right? We're going to compute the max over these numbers. This max is idempotent, commutative, and associative. So we guarantee that, it doesn't matter if we observe the 1, the 2, the 3 first, as long as these updates are delivered. And as long as we have an anti-entropy protocol to say, well, let's say that some of the messages don't get delivered, a replica that does have all of them can basically send its state and repair it. As long as we have a repair mechanism and an anti-entropy mechanism in the system, we can guarantee that we have correct conversions of this object. So this is a trivial example. If you have natural numbers, you compute max over it, that's great. Nobody builds an application with just natural numbers and max, unless you're building a distributed counter service, as Joe Blumstead likes to talk about all the time. So CRDTs, so we'll look at a more complicated example. So one of the ones that is basically one of the core data types that you can build everything in terms of is something called the observe remove set. So the observe remove set is a set that allows arbitrary additions and removals from a set of a number of an item. It could be added, removed, and it properly captures causal information in the object itself so that we guarantee correct convergence. So we're going to walk through an example. It's going to be pretty complicated, but you'll get the general gist. I mean, it's complicated if you've never seen CRDTs before. So here we have 3 replicas. We have a distributed execution. This is the final state that the replicas have, and this is metadata associated with the object. So we're going to assume at this, this. So these things are the metadata, the oval, whatever these shapes are. Yeah, see, like math, good. Shapes, bad. Like algebra, good. Geometry, bad. So yeah, so these are the states at each replica. And this above is the metadata that's associated with each object. So we'll say at this time here, we have concurrent additions of the item 1, and we track it via a unique identifier. So we say 1 was added. We have 2 sets. So this is a 3 tuple, if you're familiar with Erlang. And this 3 tuple says that item 1 exists in the set with the add unique identifier B and no removes. And we say, well, we concurrently added 1 at A here, at replica A. So we insert unique identifier A into the add set. We have no removes and 1, right? So now, when these 2 objects merge, eventually, we know that we've tracked 2 additions of 1. So we're allowed to remove things that we've already added, right? So now we move to the second stage here. We do some replication, and we see that here we remove B, and then we propagate the state over here. So now 1's still in the set over here because it observed the 1 addition at time A and the removal at time B, right? And then finally, when we get here, we merge everything together, and you see that the metadata is all the same, right? So this metadata is a grow-only set of metadata. It's a set that we can just union that information in. And then when you remove something, you only remove the additions that you've observed, right? So this differs than a sequential execution of a set, because in the sequential execution, you don't have this concurrency anomaly where you have a concurrent addition and removal of an item, and you have to decide how you reason about it. So most of these data structures are very similar, but they have biases that need to be placed in the system, in the resolution, to make it deterministic. So you have to have a bias that says, well, in the event I have concurrent removals and additions, I have to choose one or the other. So you can either bias towards the remove, winning, or you can bias towards the add, winning. And each of these are useful in different cases. Usually the add bias is the one that people like the most, because it makes the most sense when you think about a system. You're usually, you reason about a distributed system, you'd say, well, if I talk to that node over there and I say remove this thing, and I concurrently have an addition over here, the addition probably should win, because I'm usually not going to remove things that I haven't seen yet, right? So the add one seems to make the most sense. So what is interesting here is that composition of these data types is non-trivial. We have seen this with the map. The map allows this arbitrary composition. So Russell Brown at Basho did a ton of work on this, spent a very long time. It involved a bunch of researchers in Portugal and France. And Sean worked on it. Sam Elliott, an intern, worked on it. We threw a lot of resources at this, because composition in the map is not trivial. Because you have this metadata that flows through this object. So you can't just stick another CRDT in there without properly mapping the metadata from the object that's being composed into the composer, essentially. So we'll see kind of an example. So what do we mean by composition? So CRDTs gave us this property that allows us to have these independent things happen in the system. We can have these happen on mobile devices. We can have these happen on Internet of Things devices. We can do these things, compute these things, and then join them together. That's great. How do you build a program with that? Well, you have to compose CRDTs. The composition of a bunch of CRDTs is a bigger program. And we're going to show that this metadata mapping is not trivial. So here we have a thing. So we have replica C, and we have its timeline. And then we assume that we have a function here that's going to take a value x, return 2. So this is just a function that basically maps 1 to 2s. And we make it very simple. And we're going to have this represent the path of the composition here, right? So we say that at time 1, we have 1, and we map it to 2. But we don't map the metadata. So let's talk about, we're not going to map the metadata yet. So we're going to say, OK, now we have the empty set. We map it, fine. OK, so if you actually do the mapping at every stage in the CRDT's evolution, you will get convergence. It will be, you will get a correct answer, but you will not be able to converge them. So if we want to take a look at a more complicated execution, this is the one that we looked at before. So this is the one I explained about 5 slides ago. So you should be familiar. We have the set. We do all these concurrent things, and we end up with the result. So here, we're going to take node B out just to make this simpler. So we're only going to look at the communications and concurrent operations happening between C and A, because C and A are the ones that do these concurrent additions, and C has the removal that happens. So we have the addition concurrently. We have the synchronization with the removal here. It stays here, and then we do this. OK, so now we add our function application here. So fine, we do get the correct result at the end. This does work, right? If we map from one time to the other time at every single possible time step, and we assume that this is a synchronous mapping between these two, which it's really not going to be, because we know how real computers work, we know that this is going to be OK. And these will be easily able to be rebuilt. We can rebuild these. We can replay this f of a. That's fine. We can replay this f of r of c. Fine, again. But what we don't have is we don't have the strong eventual consistency property on the composition. Since we didn't map this metadata through correctly, we end up with objects at the end that are unmergeable. So now I have, so if this update here had not happened and I had the empty set here, well, now I don't know if this 2, if I had an empty set here and I propagated the empty set and I had 2 and empty, I don't know if that empty set observed the addition of the 1 that got mapped to 2, or if it hadn't seen it yet. Because this information, this metadata, is what's important to understand how to do this mapping, how we resolve it. This metadata captures logical time, essentially, logical time of updates in this system. Okay? Does that make sense to everybody? That was OK, clear? Wrote the diagram like 6 times. Wasn't sure if anybody would understand it. I don't know. There's a couple people shaking their hands. Sean gave me the thumbs up, so that's good. OK. So composition, not trivial. And there's this difference because this set has a value that's non-monotonic, right? We can't reason about monotonicity on the value because the set can go up and can go down. So if we have a set where we only ever add things, that's fine. We use union at the end. It's fine. We need no metadata. But in a situation where we have a value that has a non-monotonic change, it can basically vary over time, that's problematic. But what CRDTs do provide is they provide monotonic growth in state. We always know that we're accumulating more information about this object's change over time. So we'll always know if we see something, and even if the value is a lot less, we know if it came afterwards in time, and it observed something and then forgot and then got rid of it, right? So we can determine the difference between not being present and it was present and it's no longer present because I removed it. So in this example I gave you, you might say, well, that's fine. We can write this function to map the metadata. This mapping of the metadata is non-trivial. We found this out because we've tried it a bunch of times. In this research, we found out it gets really complicated when you start doing things with folds and other types of data structures and products and unions. And we're going to see all of that shortly in the talk. And finally, if we do not have this mapping metadata, the objects are essentially unmergeable. They are mergeable, but you won't get the right result. Or rather, you'll get a result that's defined by the function that does the merge, but you won't get the desired result, right? A correct result. So for any of you who are interested in the research kind of that led to this, this idea, we have this paper that is an abstract with an associated talk from Russell Brown, and me and Sean were involved, which talks about how to do this composition of a dictionary. And it's basically, this is the React-DT map provides us. This is an open source library in React-DT, which provides a bunch of implementations of CRDT. You can use them. It's on our GitHub. It's free. Yeah, you should use that because the libraries are badass. There's a second paper by me that talks about how if you break the map apart and you want to store it in independent pieces, that composition is non-trivial without doing the metadata mapping correctly. And finally, if you're familiar with Neil Conway's work on Bloom at UC Berkeley and Joe Hellerstein's group, in their paper where they talk about extending the Bloom system to logic and lattices, which does a very similar thing, they run into similar problems as well when they talk about, so they have a section where they discuss problems with the approach of doing it with CRDTs and kind of this scope dilemma that they talk about and how this composition of things doesn't necessarily guarantee correct merging. So these are 3 very important resources. I highly recommend Neil Conway's paper that was at SOCC 11. OK. All right. 39 out of 133 slides. Let's talk about LASP. We're going to talk about this very little, actually, and we'll talk a lot more about how it kind of fits into the ecosystem. So LASP is essentially lattice processing. Clever name, right? List processing, LASP, lattice processing. I don't know. The acronym doesn't work out 100%, but at the time that we came up with the acronym, we thought it did. That's what happens when you're working all night, right? So, so essentially what we want to do is we want to provide a system, a runtime, for centralized and distributed executions that supports this composition of metadata. So again, we want it to have both centralized and distributed semantics. So under the centralized semantics, we assume that an anti-entropy protocol isn't needed to repair things. We assume synchronous delivery of messages. We assume asynchronous delivery of messages between communicating processes on the Erlang VM, which has synchronous delivery to the mailbox, I believe. And we also assume that we never have to repair things. So we never assume that like the updates are going to come out of order, even though we're tolerant to it. You don't have to assume this in the central semantics for the language. So we'll walk through an example here. So we have a replica, and then we have a function applied to the replica. So again, this should be a very familiar slide. You've seen it a bunch of times already in this talk. So we have here the sets in 1 with b. Then we remove it. We get the add at time b, and then the removal at time b. Then we have here the addition of time a, and this is left out because, yeah, this is a copy and paste error, but you get the general idea. And when we apply this function, what we do is we essentially map this through. So we map the metadata through, and we basically change the value in the set, right? So this is an observe remove set that we've talked about that tracks additions and removals. We map the metadata through. So in the map case, it's very trivial, because all you have to do is change the value. It gets a little bit interesting if you have a function that will map to a smaller codomain, because that means that some things are going to map into similar things in the codomain, right? So in that case, we have to identify things that already exist in the metadata and then union the metadata. But that's still pretty simple. It gets really cool when we talk about distributed semantics. So when we look at distributed semantics of these, what we want to do is have, this, which you'll never be able to follow, but you can just get the sheer magnitude of the problem, right? So here, we apply this function. This function's replicated. The replicas are replicated. And again, we assume this is at a logical time, not a physical time. And so we say, well, we perform this mapping, and then when we do the state synchronization here, and that way we assume that all this metadata is going to come out correctly and merge correctly. And in the set case, it's simply a matter of unioning in the unoptimized set. In the optimized set, it gets a lot trickier because you have to start munging the metadata a little bit. So that gets a little bit more complicated. I'm going to take a sip of water because I'm talking a lot. Finally, the system is designed in such a way that it allows for composition of the runtime system itself. So in the system itself, in the centralized execution, you have a process, you have another process, and we send data, and we synchronize over these variables, and we ensure that these lattices change, and we map this metadata correctly. In the system composition, you can basically say, well, I have this one last system running here, I have this other last system running here, and I'm going to do the metadata mapping between systems. That's fine. Obviously, right now, this is a research prototype, so we only support doing this in Erlang. We don't have another runtime. I'd love it to be like C and LLVM or something like that, because then we could compile it to all these different fancy targets and do all sorts of crazy stuff. But obviously, we don't have time for that. So this allows, through use of just a lot of parameterized modules, not actual parameterized modules, but through modules that kind of are parameterized, to basically take functions to know how to through some interface, know how to apply the updates to the other system. So, if it's over TCP, or if it's over distral, or if it's over, whatever. So we can do this cross runtime. In the centralized runtime, we assume a single node model. So we assume that it's going to be a bunch of processes running on the same VM that can operate over shared state. So all these variables that we're going to see in this language are essentially stored in shared state. And we synchronize on these variables. Now we synchronize within a VM. We don't synchronize across VMs. So that's the difference, right? Don't think that I got a multi-Paxos system here running. We basically just synchronize on variables. We wait for a variable to change. We see that time, that logical time I talk about. We see that logical time change. We know that things have happened to the system, and we can propagate changes through the system. In the distributed runtime, well, we can just think of the distributed runtime, well, it's a bunch of nodes, but at each node, I'm going to have a centralized execution, right? So we're going to have centralized execution over a data store that's either per process or per VM, and then we're going to have this synchronization happen. So the distributed one is going to assume that we replicate the data, and then those replicas of the data have a single node kind of execution. It's very similar. It's not 100% the same, and I'm happy to talk about all those details, but that's too nitty-gritty for the talk. All right, so semantics, I'm not going to talk about them a ton. We have a paper, and we have another paper that's a draft, and I'm happy to share what information I can about kind of how the details of how some of the algorithms work. We'll walk through them quickly now. But well, first, quickly kind of talk about the system model, right? So in the system model, we're going to think of each variable. So imagine a programming language where each variable represents a stream. So if I go back here for just a second, we imagine this is a stream. So replica A, this is a replica of a single object. We assume that we can think of time as a stream of values applied to some object, right? You think this should be very familiar if you think of any system that uses a log, write-ahead log, or any sort of system that uses logs for storage. So we're going to assume that each variable is a stream. And in the centralized execution, we're going to think of it like this, right? So we're going to have this replica, and we're going to have changes over time. So in a register, in a set, we're going to see that we have this metadata that moves. This metadata is always, so you think of this as a partial order, this metadata is always going to move forward. So we're going to design the system in such a way that we guarantee that it always only moves forward. So if somebody sends an update to this system, so imagine I'm here, I'm at this logical time 3. Somebody sends an update to a system with this object from logical time 1. We ignore it, right? Because we can compare object at logical time 1 to logical time 3, and we can see that logical time 3 subsumes logical time 1, right? The set, don't look at the set, look at the metadata. The metadata subsumes the other, right? So we think of objects in the system as streams that change over time and that causally advance over time. In the distributed execution, so this is the naive, super optimal kind of, we don't have any failures because this is a fake computer network model. And in this model, we have 3 replicas of the same object. And we imagine that when we write to them, we broadcast, we do a reliable atomic broadcast, and everybody gets the same objects at the same time. So we can think of a distributed execution as a replicated centralized execution. So, I don't know, we work on computers, right? And we work on real networks, and we work in like bad data centers. So essentially, we have problems of concurrency, failure, and we need anti-entropy and repair mechanisms to fix things. So let's talk about what a real execution looks like. So that looks a little bit more like a real system, right? We assume that, yeah, we have these things, they're going to synchronize, and oh man, maybe replica B goes offline and comes up with no data. Wow, that doesn't happen ever. And then, and then we basically merge state back in. So we merge state over here, we merge state over here, and we basically continue advancing of this state forward, right? And eventually we get the right thing. So this replica goes offline, comes up back with nothing. We can assume this is an anti-entropy process or a read repair process if you're familiar with like kind of the dynamo style ways of doing things in React Core. It could be handoff as well. We don't support sloppy quorums, but that handoff mechanism that was talked about in the last talk is applicable here as well. And finally, everything merges out right. So what's the criteria here? Is that if I don't deliver all the messages in the network, which I don't here, because well this merge doesn't happen, and then later it comes in here. The anti-entropy protocol ensures that all updates are observed at all replicas. This is a very important property that you need to realize strong eventual consistency. So so streams, distributed executions end up being deterministic now as long as we can guarantee the delivery of all updates. And again, it requires eventual delivery either through read repair or anti-entropy. Cool. So the semantics of the language allow you to declare variables. We're going to see an example of this, but I'm going to talk through what the general operations are first. They allow you to declare variables, set the values of variables. We can continuously set the value of a variable. We can say A is this, A is this, A is this, as long as A continuously causally moves forward, as long as it moves forward in logical time. So declare says, give me a CRDT type. I'm going to initialize the state at the bottom value. So these are semi-lattices, and we have bottom values. And for a set, for sake of argument, we can just say this is an empty set. For a counter, we'll assume 0, right? Bind allows us to assign a value to a stream, so to add another value to that stream. So for replica A, I say bind 1. So if it's a natural number and it increases, we say bind 1, bind 2, bind 3. Bind 1 stays at 3, right? Because 3, in this, we're defining it over max. If this is that set, we would use that metadata to say, I've already observed that. I'm not going to allow the assignment again. Or I'm going to ignore it, right? Because it's assuming that, hey, that was a message that was delayed on the network. I've already seen it, so because I got it from somebody else. We allow you to read variables, but we can't allow you to just read them at any point, because that sacrifices determinism. You might read it when it's 1. You might read it when it's 4. So how do I build an application that knows how to read it and end up being correct? So if you're familiar with the LVARs work, there's this idea of a threshold read. Threshold reads assume that you know a priori how the data structure is going to change. In a real system that's distributed, we don't know this, especially if it's stream processing. So we provide this monotonic read function, which ensures forward progress. So we can say in the system, so the determinism property that we want to get is that given a stream, and given all replicas are going to observe this stream, we want to ensure that we always read forward. We never read backwards. We're never going to read a delayed value. We're never going to read a node value. We're never going to read a repaired value. We're always going to ensure that we read forward. And if we always read forward, and we always have eventual delivery of messages, we can guarantee that all 3 replicas are going to end up with the same state. And we have some proofs about that, but they're not here. We can block on inflations, which means that I change some value. An inflation versus a strict inflation says that if I change a value and the value doesn't advance, it's still an inflation because I provided some update that did advance the causal state, but necessarily didn't cause like the value to increase or the value to move forward in logical time. strict inflations ensure we always read a newer value. And we build all of our primitives in terms of this. So we have algorithms for the monotonic read. I don't have time to go through them, but they're there. In terms of these compositions we talk about, like this map function we've been talking about for most of the talk, we block for changes in inputs using that monotonic read function. So we say, read this stream, but don't return to me until it's a newer value than I previously observed. We compute some delta over that change to apply it. We map that metadata through, and then we propagate that change. So if I map A into B, I see A change. I map the metadata through. I assign B, and then I basically wait on A again. So we model these things as processes in the system. These processes are replicated. So in terms of functional, what do we have? We have a map. We have a filter and a fold. Fold's really complex. We got some algorithms. Here's one. That's like really Monty Python, right? Like, and so here is kind of the simple example we talked about. We map the metadata through, and we see that the object advances in the same way. And on a single execution, we guarantee these things happen together. We have a filter. We have a fold. Finally, set theoretic. We have product intersect. I'm running a little behind, so I'm trying to pick up speed here. So we have set theoretic operations as well. We have products, intersections, and unions. So you can take sets and compute Cartesian products. You can build intersections, unions, all the stuff. That maps the causal data through, too. So those are pretty cool. So the architecture of the system. So LASP is built on, it's built on React Core. It relies on using a shared variable store. So if you have two programs that are going to synchronize on some data that's changing, we require there being a shared place where we can store that data on a node. We have support for LevelDB, Bitcask, and ETS. So ETS was really good until we needed to save things. So then we, you don't need to save things in evaluations, but them, in LevelDB and Bitcask, we have persistence. We use CRDTs provided by ReactDT, so thank you to all of the great contributors to ReactDT who are in the room who built these great things that I can build all this stuff on top of. I really appreciate your support. And finally, for the centralized semantics, we're going to have these processes operate directly on the variable store, so it goes through some abstraction layer to ensure things happen correctly, and then we synchronize on these variables. In the distributed model, we're going to basically replicate and shard that store. So if you were in the previous talk on React Core, Mark was saying that you kind of use this consistent hashing function to determine the placement of all these replicas of objects across a system. And you have these membership protocols that allow you to move things around and do dynamic membership and handle failure. We do the same thing. We basically take these variables and we break them up. We also have a mode where we can basically create copies of them and co-locate them together if we want to do an optimized execution that has less network communication. We use React Core to do this. I'm not going to talk about React Core because you probably heard about it 100 times. We use quorum requests, which basically ensure that we read and write to majorities. And then we have an anti-entropy protocol, which is core to making sure that we have all replicas observe all updates when we can drop messages. Again, we have a hybrid model as well, which basically replicates centralized execution. So you can have the variables spread out all over the place and have, do your computation across all these different nodes. Or you can basically say, well, I want to ensure that all of these things are co-located on one partition because I need it to be fast. So we have this hybrid model where you can play around with how the distribution works. Doesn't change the semantics. It doesn't change the semantics because the semantics are written using the harder one where variables are in arbitrary locations. So we'll talk about some examples quickly. Here's a sample of the language. So we declare a variable. We assign it to S1. This gives you a unique ID back for that variable. This update function takes, for the purpose of the prototype, it takes operations applied to CRDTs. So this uses the ReactDT interface here. So this is add all says that so I declare this should be a set. Screwed up in the slide, whatever. We say update. We're going to update this S1 that we got back here. We're going to add elements 1, 2, 3 to the set. And A is the actor. So I've just put some dummy value in there. But what you want to do is use unique identifiers to properly identify concurrency in the network. So this could be whatever. And then we create a second set, and then we can map things. So we say I have S1, which is the starting set that I've added 1, 2, and 3 to. I want to apply this multiplication by 2 function, and I want to put the result in S2, which is also a set. So pretty similar. To normal Erlang kind of map stuff, this declare thing is something that you have to do because it's, we have to say, well, go out to the network and make this variable on all these replicas. So this is what the language kind of looks like. The centralized execution uses a module called LASP core, which the other one calls into. LASP core takes a store variable. This is a reference to a system on disk. So this would be either a LevelDB reference or a Bitcask reference. So LevelDB magic binary, Bitcask reference, or ETS table name. In this case, this is how we would run on a centralized execution. So we can have the programmer write in this language, and we can easily compile to this language given a store, right? So that's nice. And we can also compile Erlang to this. We don't do that because that's kind of a trivial compilation exercise, but that's essentially the ultimate goal. Or go to the Erlang AST. All right, so let's talk about a real-world kind of thing that we're trying to build. So we're trying to build an advertisement counter. This advertisement counter is going to track impressions. So everybody here has a mobile device. You all have Angry Birds for some reason. That's weird because we're all in the same room. And everybody gets a list of advertisements. So while you're playing the game, you get ads. We're going to count how many times you see certain ads. So you're going to see some ads from Rovio. You're going to see some ads from Erlang Solutions. And we want to count the number of impressions. So these clients are going to go offline, and they're going to continue to see ads, and then we have to synchronize. So we can't use a normal counter, because if we use a normal counter and it's like 2 and 2, do I add them? Well, I don't know, because he might have already seen my 1. So right, it might be 3, it might be 2, it might be 1. How do I know? So what we need to do is ensure it's deterministic. We want to disable the advertisement on all the mobile devices when it's seen by 50,000 impressions. And we want to push that state to the client. So we're going to talk about one possible monotonic design that ensures that it converges correctly, requires no synchronization, no global synchronization. Clients have to synchronize with like the centralized data store, which stores the ads. So this is how the information flow looks. So the information flow says we start out with some ad counters here. So we have individual ad counters, these 2 counters. And this might be not too big, I apologize. We union them into this set. That's the set of all ads. And we do this for Rovio, and we do this for Riot. Let's pretend these are the 2 people displaying ads. What we do is we then union these. So we union these, and then we're going to basically join them with this contracts thing. So contracts say this is like a thing that says I should display this ads, right? So you'll assume that we have 100 ads, maybe 50 of them have contracts. So this is like a join. You just imagine this is an inner join in a database, right? You're going to like kind of join the contracts with the advertisements. And then so this here is going to compute the Cartesian product, and then we're going to apply a filter to say where the IDs are equal. So in SQL, think about how a SQL engine works. It joins, computes a Cartesian product. It doesn't really do this in the implementation, but in relational algebra, you do a Cartesian product, and you apply some filter on the product where the IDs are equal. Conceptually, that's how it makes sense, right? And then essentially, we push these ads out to these clients. These clients are going to read these ads, and then every time the client gets an increment, it's going to increment a local data structure that we send to it. And then that data structure is going to be propagated back occasionally. So how often do we do this? Well, this is a measure of divergence. If we want to allow clients to display ads more than they should, that's fine. You can make the synchronization window small. Each client just has to check in periodically. If you want to ensure that the divergence is small, they have to check in more frequently. If you want to ensure that the divergence is bounded, you need to basically also send a maximum number that that client can send. But this design is synchronization free. So essentially, when this counter hits 50,000, a process sends a thing to remove it from the set of displayable ads. Or maybe it changes the context. And then we basically recompute. So this red path shows that we have this update come in. It triggers this read. And then we basically repropagate the state. And that all is monotonically advancing state. It's all logically time moving forward. It requires no synchronization. If messages are delayed, dropped, or reordered, the algorithm is correct. And it works. So now it's just how you reason about divergence. Oh, man, running low. So anyway, monotonic design. Metadata to prevent duplication. So I'm almost done, actually. I'll have to skip related work, but you can talk to me later about that. So in this design, what we really like here is that this is how you would normally think about distributing it, right? We would say server processes, client processes. Yeah, man, the server-client model, right? But we don't need to do that. We can do this, right? Because we can guarantee that at these boundaries, these communications points, we use these data structures that allow us to reorder things and compose these things, reorder things, handle duplication, handle repeated message delivery, handle all this great stuff. So all we have to do is ensure at these message boundaries here, we use a data structure that handles this correct metadata mapping. And that's really nice. And this can be, I don't know. So yeah, I was at dinner the other night, and somebody was like, hey, that's a microservice. And I was like, I don't know what microservices are, but cool. Like, so yeah, that's great, right? So that's an interesting thing. So we can move this state around. So in our, going back to our Internet of Things, we say that this is the centralized server. This could be some edge routing node maybe, or maybe it's on the centralized server as well if we go to this one. This could be at some core node, and these could be the clients. Or these could be the mobile clients, and this could be the server, right? The architecture allows us to arbitrarily distribute the graph. So I'm running really low. There's some code. It's all on GitHub. It's in my slides. The slides will be online. You can look at it. You can bug me. I'm happy to talk about this all the time, because it's all I think about. And this is the code to do the entire ad counter, essentially here. We set up some state, except for the server, which disables the ads, and the client, which displays them. We say, we make some ads, we join them together, we start some servers, we start some clients, and that's it. right? So there's not a lot of time to work, but the related work is distributed Oz. We've written up a lot on this, so I can send it to you. Durflow was our first work. BloomL is related work that does logic programming without CRDTs. LVARS is works on single node, kind of this architecture on a single node with threshold reads, which assumes a priori knowledge of state change. dstreams is similar because it applies kind of probabilistic techniques and it can handle like duplication, message delivery, and all of this fancy stuff. And finally, it realizes streams and batches of changes, which is very similar to the model that we use. And finally, Summingbird is a work from Twitter that uses commutative monoids, which is very similar to ours, which are commutative idempotent monoids, to basically ensure that we can handle all these weird delivery things that happen in real networks. And finally, future work, we want to make it faster. We want to use delta CRDTs. We want to use the OR swap. We want to use operation-based CRDTs. We want to use deforestation to basically reduce the amount of computation we have to do with those big, massive tree structures in the graphs. The source is available on GitHub under my name. There's an Erlang workshop paper. There's a Eurosys paper. And finally, this work, some of the members doing this work have been funded under the Sync-Free European Research Project. So there's the EU flag. And finally, that's it. Thank you. 4519.
So we have 2 minutes for questions.
No questions? Must have been really good then, right? It's a lot, but yeah.
Okay, there's one. Over here?
Yeah. Yes.
The example of the answer, is that on the same GitHub repo?
Yes, everything is there. Yep, it's all open source. It's all available. It's all under the Apache 2 license. Yep, absolutely. Yes?
So right now, LASP, maybe I misunderstood, is LASP a language that compiles to Erlang presently, or is it a library?
Is a library. Yes, is a library. There is some work that me and Sean have specifically talked about, and Peter's talked about, where we want to basically have like a higher level language that is more expressive for doing like kind of programming of data flows, and then find a way to have a compiler basically build the programs and then distribute them. So if you think about Impala, so Impala is another related work I forgot to mention, but Impala has a similar design where they basically use LLVM to compile like portion of SQL queries, and then it distributes these binaries everywhere. So it's a similar model where we want to have custom language, go to an AST, build a bunch of fragmented programs, and then we ship the fragmented programs on the wire. So we have the fragmented program piece working, but yes?
Does this work assume any kind of static topology in the network, or joining or leaving nodes?
Yeah, so the prototype does not, so the semantics hold under dynamic membership. The handoff mechanism doesn't hand off all of the state currently because we've added a bunch of new stuff and I haven't got handoff working yet. So while it works conceptually, I just haven't had time to write the code yet, right? The AAE stuff is a little funky too. We have a really, really bad AAE process. So this is why we want to extract AAE out of KV and put it in core, because right now we have to like, our simplified model just to get the guarantees that we want in the prototype is like, we'll just send everything again, right? Like that's an AAE method. It's not great, but it satisfies the, the constraint. So.
One more question?
Okay. No?
No? All right, give
Okay.
us a hand.
Thanks. Appreciate it.